Hello friends, in this video we are going to see about the measures of some similarities and dissimilarities attributes which are going to follow while performing the data exploration. So similarity measures. Basically, a similarity and dissimilarity are very important because they are used by a number of data mining techniques such as clustering, KNN, anomaly detection, etc. The term proximity is used to refer to the similarities or dissimilarities. The definition. The similarity means similarity between two objects is the numerical measure of the degree to which the two objects are alike. Consequently, similarities are higher for a pairs of objects that are more alike. Similarities are usually non-negative or often between the zeros and 1. Next, the dissimilarity between two objects is the numerical measure of the degree to which two objects are different, and dissimilarity is lower for more similar pair of objects. Always remember. Next definition is frequently the term distance is used as a synonym for a dissimilarities. Dissimilarities sometimes fall in the interval of zeros or 1, but it is also common for them to range from 0 to infinity because we cannot count the range of distance. See, we cannot say we are going to the far away. Far away means how far away, that is we don't know, right? So that is also one of the uncountable amount of distance we have, right? Next is proximity measures. So what are the proximity measures are? Proximity measures, especially similarities, are defined to have a values in the interval of zeros and 1. If the similarities between the object can range from 1 or 10, then we can make them fall into the range of 0 to 1 by using the formula S dash equal to S minus 1 divided by 9, where S and S dash are the similar originally and the new similarity values are respectively. Fine. So S means the original value. Fine. And S dash is the new similar value which are going to get. Next is the more general cases. S dash is calculated as S dash is equal to S minus mean of S divided by max of S minus mean of S. So where mean of S and max of S are the minimum and maximum similarity values respectively. Next, likewise, the dissimilarity measures with a finite range can be mapped to the interval of 0 to 1 by using the formula d dash is equal to d minus mid of d divided by max minus mean d. It is the same. See, there is no difference basically. When you are working with the similarities, we are working with the similar measures, and when we are working with the dissimilarity, the proximity measures are same, just we are dividing it with the mean with the max. That's it. If the proximity measures originally takes the value in the interval, that is 0 to infinity, then we usually use the formula d dash is equal to d divided by 1 plus d. For such cases, bring the dissimilarity measures between 0 to 1. The similarity and dissimilarity between the simple attributes. How we can do that? The proximity of an object with a number of attributes is defined by combining the proximity of individual attributes. Fine. So we are doing it for the individual attributes. Attributes mean any field we can say, right? So the attribute types and the similarity measures are considered for an interval or a ratio of attributes. The natural measure of a dissimilarity between the two attributes is absolute difference of their values. Consider, we might compare our current weight to our 1 year ago. In such cases, The dissimilarity range from 0 to infinity, right? So the range can be differ, right? The previous weight and the current weight is somewhat differ also, right? Next, for an object described with a one nominal attribute, the attribute value describes whether the attribute is present in the object or not. Comparing two objects with a one nominal attribute means comparing the values of this attribute. In that case, the similarity is traditionally defined as a 1 if attribute values matches, as 0 otherwise. See, if the both the objects value nominal attributes, okay, both the nominal attributes values will get matches, then we say it is a traditionally 1. After comparing those objects, we say it is 1. But if it not matches, it is dissimilar, then we say it is a 0. In a dissimilarity would be defined in the opposite way. That means it will be 0 if it is matches, and if it is 1, that means it does not matches. That is for dissimilarity measures. Next, for an object with a single ordinal attribute. Now we have seen the nominal attributes, right? Now we'll see the ordinal attribute. So in the ordinal attribute, information about order should be taken into the account. Consider an attribute that measures the quality of a product on the scale of poor, fair, okay, good, and wonderful. That is the ordinal attribute, right? Categorical. So it would be reasonable that a product P1, which was rated wonderful, would be closer to the product of P2, which is rated as good, right? See, what we are saying that P1 is rated as what? Wonderful, right? And P2 is rated as a good, right? So we can say that, and P3 is rated as okay. So we can say that the good is much nearer for the wonderful, right, than okay, right? So we can range it. Are you getting it? Next, to make this observation quantitative, the values of ordinal attributes are often mapped to the successive integer, beginning at a 0 or 1. For example, we can say the poor is 0, fair is 1, okay is 2, good is 3, and wonderful is 4. So that we can convert it into the numerical value, and through that integer value, and through that we can perform the distancing between the each other. In the above, in the below table, x and y are two objects that have one attribute of an indicator type, that is, and dx comma y and sx comma y are the similarities and dissimilarities between x and y respectively. So now we'll see the table. So in this table, we having the attributes, that is interval or a ratio, nominal and the ordinal. So in the interval and ratio, when we are calculating a dissimilarity, what we do, we calculate x minus y with the inverse, right? But when we are calculating the similarity, what we do, s is equal to minus of d. That means the s is equal to 1 by 1 plus d. Or we can say s is equal to e raised to minus d, or s is equal to 1 minus d minus mid of d divided by max of d minus min of d. So this we do when we are working with the interval ratio. Next comes is nominal ratio. When we are having a nominal attribute, that time what we do, that d will be 0 if x is equal to y, and d will be 1 if x is not equal to y. That is for dissimilarity, which is already discussed, right? But in the similarities, if x is equal to 1, then s will be 1, and when x is equal to y, that time it is 0. It is vice versa. See, when it is equal, that time similarity is 1 and dissimilarity is 0. When it is not equal, that time similarity is 0 and dissimilarity is 1. Fine. Next, third attribute is ordinal. In the ordinal, what we are doing, we are just value mapping to the integer from 0 to n minus 1, where n is a number of values. So what we do, x minus y divided by n minus 1. And for the similarities, what we are doing, s is equal to 1 minus d. So which is easier, like what we have discussed before, that is only the given in the formula manner. Next, dissimilarities between the data objects. So how we do that? First is distance. A distance are the dissimilarities with a certain properties. The Euclidean distance, that is d, between the 2 points, that is x and y, in a 1, 2 or higher dimensional space is given by the formula. How we do that? That is d of xy is equal to root of summation of n x of k minus y of k raised to 2. That means the x from 1 to 0 and y from 1 to 0, the addition of all together and the square of it and then root of it. So on the basis of that, you can find the Euclidean distance of the dissimilarities measure, where n is the number of dimension. Fine. And x of k and y of k are the respectively the kth attributes of a x and y. Fine. Next is the Euclidean distance measure is given by the generalized Minkowski distance matrix shown as, see, this is a matrix given where we are working with the summation of n x of k minus y of k into r with the 1 by r, that is divided by 1 by r, where r is a parameter. Okay? The following are the three most common examples of Minkowski distance. Minkowski is one of the author who has designed those distances. Through that, we can elaborate the different formulas for our data sets. So, consider R is equal to 1, also known as a city block like Manhattan or L1 norm distance. A common example is the Hamming distance, which is the number of bits that are different between two objects that only have a binary attributes. Fine. R is equal to 2. That time we can say the Euclidean distance, that is L2 normalization. Next is R2 is infinite. That time we can say the supremum. That means L is a max or L is an infinite normal distance. And this is a maximum distance between the attribute of the object, and the L of infinity is defined by the limits value. Through that you can define the value of L of infinity. Next, we have given one table where points are given, x coordinates are given, and y coordinates are given. And they are saying that R should not be confused with the number of dimension or attributes of n. Now what we are doing? L2 distance. So when we do the L2 distance, we get this values for the P1, P2 and P3. Then when we do the L1 distance, we'll get this values with the help of formulas. Then when we do the similarities between the data objects, now we'll see the dissimilarities we have seen previously. Now we'll see the similarities between the data objects. So how we can do that? See, x and y is the similarities between the points x and y. Then typically we will have that s of x is equal to x and y is equal to 1 only if the x is equal to y. But if it will be s of x comma y and s of y comma x for all x and y when it is symmetric. Fine. Non-symmetric similarity measures, that is confusion matrix, very important. Consider an experiment in which people are asked to classify a small set of characters as they flash on the screen. The confusion matrix for this experiment records how often each character is classified as itself and how often it is classified as another character. For example, suppose 0 appears at 200 times, was classified as a 0 160 times, but O 40 times. Likewise, suppose that O appears 200 times and was classified as a O 170 times and O as a 30 times. Fine, that is a example they are given. Now, If we take this count as a measure of a similarities between the two characters, then we have the similarity measures, but not a symmetric one, because 0 and O, that is 40 divided by 2, we are calculating. And for the second time, when 0 is there and O is there and 0 is there, that time 30 is your possibility, right? So the symmetric value will not get, because first time we are getting 20 and second time we are getting 50. So in such situation, the similarity measure is often made the symmetric by setting s dash x of y and y of x as x comma y plus y comma x divided by 2. So we'll get the answer as 17.5. Next, for the binary data. Similarity measures between the objects that contain only the binary attributes are called as similarity coefficients and typically have the values between zeros and 1. A value of 1 indicates that the two objects are completely similar, while a value of 0 indicates that the objects are not at all similar, right? See, 1 means what? Both are similar, because that is in similarities. And 0 means what? The objects are not similar. Be in that mindset, okay? Next is, let x and y be the two objects that consist of n binary attributes. The comparison of two such objects, that is two binary vectors, lead to the following four quantities. Frequencies like f00, the number of attributes where x is 0 and y is 0. When f01, that time we can say x is 0, y is 1. When f10, that time we can say the frequency value of x is 1, y is 0. And when f is 11, so x is 1 and y is also 1. So, simple matching coefficient, that is SMC, one commonly uses similarity coefficient, which is defined as number of matching attribute values divided by number of attributes. So f11 plus f00, that is the matching values x and y, right? And others are the dissimilar attributes. This measure counts both presence and absence quality. Jaccard coefficient in such situation, only the presence of an item is relevant. Suppose we want to do a basket market study. If we were to count all the items that a person did not buy, their number will outnumber the items purchased by a far, and it can compromise our study. The Jaccard coefficient is oftenly used in the type of asymmetric binary attributes. Always remember, it gets used only with the type of asymmetric, not for the symmetric values. How we calculate that? The number of matching presences divided by the number of attributes that not involves the 0 matches. So we can say f11, f11 plus f10 and f01. Then cosine similarities. The documents are often represented as vectors in which each attributes represent in the frequency with which the particular term occurs in the document. Even though the documents may have the thousands or the 10,000s of words, and each document is a sparse since it has a few non-zero attributes. Therefore, the similarity measures for the documents need to be ignored, that is 0-0 matches, like you do in the Jaccard measures. But must handle that non-binary vectors, right? And the cosine similarity is the most common measure of a document similarities. If x and y are two documents, then what we'll do with the cos x? Where xy and x of yy. So where indicates that the vector product x dot y is equal to the summation of n of k, x of k into y of k. And also we are calculating the vector length also using the summation and the root of a x of k square. Fine. Next. Cosine similarity is a measure of angle between the x and y. Thus, if the cosine similarity is 1, the angle between the x and y is 0. And x and y are the same except for the magnitude. Always remember that x and y is the same when you are having a magnitude. If the cosine similarity is 0, then the angle between x and y is 90. Then they do not share any terms. Correlation. The correlation between the two data objects that have a binary or a contiguous variable is a measure of a linear relationship between the attributes of an object. More precisely, the Pearson correlation coefficient between the two objects x and y is defined by the following equation. See, what does correlation means? The relation between the two objects that have a binary or a continuous values is a measure of a linear relationship, right, between the two attributes of object. So that is called as correlation. So one of the correlation is Pearson correlation, and that we can calculate with the help of this formula, that is variance of covariance of x and y, standard deviation of x into standard deviation of y. Always remember this. So we can say s of x comma y divided by s of x into s of y, where the standard statistical notations are used. So covariance x comma y is s of x is equal to 1 by n minus 1 summation of n of k, that is x of k minus x bar and y of k minus y bar. Standard deviation, how we calculate x of k minus x of mean. Then standard deviation, how we'll calculate that y of k minus y of mean in the bracket square summation and 1 by n minus 1. Now, perfect correlation. Correlation is always in the range of minus 1 to 1. A correlation of a 1 means that x and y have the perfect positive relationship, linear relationship. That is, x of k is equal to a phi of k plus b. The following two sets of values for x and y indicates that cases where the correlation is minus 1 to plus 1, where x is equal to minus 36036 minus 6. So the both values are almost similar. This time also we having positive and positive values. Next is, correlation measures are only useful when the relationship between the attributes is linear. So if the correlation is 0, then there is no linear relationship between the two data objects. However, non-linear relationship may still exist. For example, see, minus 3, minus 2, minus 1, 0, 1, 2, 3. Then 9, 4, 1, 0, 1, 4, 9. The relationship between the x and y is correlation is 0 because both are having one is having positive values, one is having negative values. So we can say that correlation comes as 0, right? So we can say that this relationship is not a linear relationship because they are not forming a 1. Fine. So in this video, we have seen some similarity measures as well as some dissimilarity measures, and on the basis of that, we are also gone through some correlation matrix and covariance of a matrix. Thank you.